Hello everyone, I am G. Hema Vaishnavi from SRM University, and today I am excited to share my Emotex internship experience on embedded systems. My project focuses on simulating a washing machine using PIC Lab. Here's a quick overview of my presentation. I'll start with a basic introduction to embedded systems, what they are and where they are used. Then I'll talk about the types of embedded systems and the programming language embedded C, which plays a crucial role in writing firmware for microcontrollers. I'll introduce the PIC16F877A microcontroller used in my project and explain the key peripherals. I'll also walk you through the software tools I used, including MPLABX IDE and PICSIMLab for simulation. After that, I'll present a live demo of the washing machine simulation project and wrap up with the key takeaways and conclusion of my internship experience. Now let's look into the introduction. What is an embedded system? An embedded system is a computer system that is built into a larger device to perform dedicated functions, often in real time using a microcontroller or microprocessor along with necessary hardware and software. It is designed to operate with minimal resources and is optimized for specific control tasks in devices such as washing machines, cars, medical equipment, and industrial machines. Unlike general purpose computers, they are optimized for specific control functions, often with real time performance requirements. These systems typically include a microcontroller or microprocessor, memory, input or output interfaces, and software all working together in a compact form. Due to their efficiency and reliability, embedded systems are widely used in everyday devices. For example, they control the washing cycle in a washing machine, regulate temperature in air conditioners. Embedded systems are classified into two main ways based on performance and functional requirements, based on the performance of the microcontroller. Based on the performance and functional requirements, there are four types: real time, standalone, networked, mobile. Real time systems respond with strict timing, standalone systems work independently, networked systems connected over a network, mobile systems used in portable devices. Based on the performance of the microcontroller, these are divided into three types: small scale, medium scale, sophisticated. Small scale use 8 by 16 bit microcontrollers like PIC16F877A used in my project. Medium scale use 16 by 32 bit controllers for more features. Large scale or sophisticated use high end processors and OS. So, my washing machine simulation is a small scale, soft, real time embedded system. Now, let's look into microprocessor versus microcontroller. A microprocessor is just the CPU used in general purpose systems like laptops or desktops. It needs external components like RAM, ROM, and input output ports to work. A microcontroller, on the other hand, is a complete system on a chip. It has a CPU, memory, and peripherals all built in, ideal for embedded systems like washing machines. So, in simple terms, microprocessor is powerful brain, needs help from other chips. Microcontroller is self-sufficient mini computer for specific tasks. In my project, I used the PIC16F877A microcontroller because it integrates everything needed to control and simulate a washing machine effectively. Now that we understand what embedded systems are and how they are classified, let's move on to a key part of developing them, the programming language used. That brings us to embedded C, the language used to program microcontrollers and control the hardware effectively. Embedded C is a specialized version of C programming language used to develop software for embedded systems. It includes all core features of C like data types, operators, but adds specific extensions to directly interact with hardware components such as memory mapped registers, input output ports, and peripherals. These additions allow programmers to control microcontrollers effectively and write programs that interact with the physical world. In embedded systems, embedded C is used to write firmware that runs on microcontrollers. For example, it can control the washing machine's motor, respond to button inputs, display messages on an LCD, and trigger a buzzer. Unlike general C programs that run on PCs with OS, embedded C programs run directly on the hardware with no OS, requiring the programmer to manage memory and timing manually. In C programming, data types specify the size and type of data that a variable can hold. In embedded systems, using the correct data type is crucial because memory and processing power are limited. Every byte counts. In C programming, data types are mainly classified into three categories: primitive types, derived types, user defined types. Primitive data types, also known as fundamental types, these are the basic building blocks used in C programs. They include int for integer values, char for characters, float for decimal or floating point values, double for double precision floating point numbers. In embedded system, these types help define variables like timers, counters, or input states. Derived data type. These are built using primitive types. Common derived types include signed, unsigned, long double. Signed. By default, data types in C are signed, meaning they can store both positive and negative values. For example, a signed int can store values from around -32,000 to +32,000 depending on the system architecture. Unsigned. If we use the unsigned keyword, the variable can only hold positive values, but the upper range doubles. This is very useful in embedded systems when we know the value will never be negative, like counters, timer values, or digital sensor outputs. Using unsigned also saves memory and prevents error due to negative values. Long and double. The long modifier increases the size and range of an integer. A long int can hold larger values than a normal int. Similarly, a double data type is used for decimal numbers with higher precision than a float. And if even more precision is needed, we use long double. User defined type. They are created by the programmer to simplify code and group related variables. They include arrays, struct, union, enum. Arrays, a collection of elements of the same type. Struct, to group different types together. Union, to store different data types in the same memory location. Enum, for naming integer constants. For example, struct can group LCD settings or timer configurations in one place, making code cleaner and easier to manage. So, understanding and choosing the right data type, whether basic, derived, or user defined, is essential in writing efficient embedded C code, especially for memory limited microcontrollers. In C programming, operators are symbols used to perform operations on variables and values. Based on the number of operands they work with, C operators are classified as unary, binary, and ternary. Unary operators work on a single operand. They are commonly used to modify or evaluate a variable's value or condition. Examples of unary operations include increment, plus, plus, and decrement, minus, minus operators, which increase or decrease a variable by 1. Unary minus means changes the sign of a value. Logical NOT, which inverts a logical condition. Binary operators work on two operands and are the most frequently used in C programs. They are divided into several types based on the kind of operation performed. Arithmetic operators like addition, subtraction, multiplication, division, and modulus, which are used in mathematical calculations. Relational operators like equal to, not equal to, greater than, and less than, which are used for compare values. Logical operators like and, or, which are used in decision making to combine multiple conditions. Bitwise operators, which work at the binary level of numbers, used heavily in embedded systems for register and port operations. Assignment operators such as equal to, plus, equal to, etc., which are used to assign values to variables or modify them. Ternary operator. C has only one ternary operator, often called the conditional operator. It is the shortest form of an if-else decision. It evaluates a condition, and based on whether it is true or false, it returns one of two possible values. Ternary operators are very useful when we want to make a simple decision in a single line without using full if-else statements. Conditional statements in C are used to make decisions in a program. They allow the program to choose different paths of execution depending on whether a condition is true or false. In embedded systems, conditional statements are crucial. For example, to check if a button is pressed, if a sensor value exceeds a limit, or if a timer has expired. Based on these conditions, the microcontroller decides what action to take, like turning on a motor or activating a buzzer. If statement. The if statement checks a condition. If it is true, a certain block of code is executed. If not, it is skipped. For example, in my project, an if condition can be used to check whether the start button has been pressed to begin the washing cycle. If else statement. This allows the program to execute one block of code if the condition is true and another block if it is false. Else if ladder. When there are multiple conditions to check one after another, we use an else if ladder. This is useful in selecting between multiple modes in the washing machine like washing, rinsing, or spinning. Each mode can have its own condition. Switch statement. The switch statement is a cleaner way to handle multiple fixed values of a single variable, like keypad input or selected program mode. For example, each button in the washing machine can be assigned a number Based on which number is read, the switch statement decides which function to perform. Loops in C are used to repeat a block of code multiple times until a specific condition is met. For loop, best when the number of repetitions is known, like running a motor for 10 cycles. While loop runs as long as a condition is true, useful for waiting until a button is pressed. Do while loop, similar to while but guarantees at least one execution, useful for means at initial setup. Now that we have seen how logic and repetition are handled using conditions and loops, let's look at the heart of any embedded system, the microcontroller. In my project, I used the PIC16F877A, a popular 8-bit microcontroller that controls all hardware actions in the washing machine simulation. In this internship project, the microcontroller used is the PIC16F877A, a widely used 8-bit microcontroller from Microchip Technology. It is part of the PIC peripheral interface controller family and is well suited for beginner to intermediate embedded system projects due to its rich set of features and ease of programming. The PIC16F877A comes with 40 pins and 33 input-output lines, allowing multiple external device connections, 8K words of flash memory, 368 bytes of RAM, and 256 bytes of EEPROM. Built-in peripherals like timers, analog to digital converters, serial communication modules, and PWM. Operates in the range of 2 volt to 5.5 volt with low power consumption. Programmable in embedded C using tools like MPLAB IDE and a PIC programmer. This is the pin diagram of the PIC16F877A microcontroller, which has a total of 40 pins. Out of these, 33 pins are input-output pins, which can be used to connect various peripherals. The pins are grouped into port A and port E, each with specific functions such as analog input, digital output, or specific functions like PWM and UART. Important pins include power supply pins, reset pin, and oscillator pins for the clock signal. Understanding the pin diagram helps us decide which pin is to use for which component, ensuring proper interfacing in the simulation. Now that we have seen the pin layout of the PIC16F877A microcontroller, let's look at how we used these pins to connect peripherals. Peripherals used in this project are LED, digital keypad, CLCD, buzzer, fan, and timers. Let's look into LED. An LED is a semiconductor device that emits light when an electric current passes through it. Unlike regular bulbs, LEDs are energy efficient, compact, and available in various colors. In embedded systems, LEDs are commonly used as indicators to show the status of operations, errors, or modes of a system. They are output devices and are connected to the microcontroller's digital output pins. When a microcontroller like the PIC16F877A sets the output pin high, current flows through the LED, causing it to glow. Now let's move to the next peripheral, tactile switch as digital keypad. A tactile switch commonly used in embedded systems is a small momentary push button that completes an electrical circuit when pressed. Multiple tactile switches were grouped together to function as a digital keypad, allowing user input to control the washing machine simulation, such as starting the cycle or selecting modes. Each tactile switch acts as a digital input device and is typically connected to the microcontroller's GPIO pins, general purpose input output pins. When pressed, the switch pulls the input pin low or high, and the microcontroller detects this change using polling or interrupt methods. Next peripheral, CLCD. CLCD, Character Liquid Crystal Display. A character LCD is a widely used output device in embedded systems for displaying text-based information. It displays letters, numbers, and symbols in a fixed grid format, such as 16 into 2, 16 characters into 2 lines, or 20 into 4, or 16 into 4. CLCDs have control pins and data pins and can function in either 8-bit mode using all data lines or 4-bit mode. The microcontroller sends instructions like clearing the screen, setting the cursor position, and data through these pins. Now let's move to the next peripheral, fan. The fan or motor in the washing machine simulation represents the drum rotation mechanism. It is an output actuator. When the microcontroller activates the motor, it simulates washing, rinsing, or spinning cycles. In simulation, the fan or motor turns on or off based on the program's logic and timers. Buzzer. The buzzer is a simple audio output device used to give audible alerts to the user. In the project, it can beep at the end of a washing machine cycle when a button is pressed or to indicate an error. It is connected to a digital output pin and activated by sending a high or low signal from the microcontroller. Buzzers provide quick and effective feedback without needing a display. Next peripheral, timers. Timers are one of the most important internal peripherals in microcontrollers. A timer is a hardware module that counts clock pulses and can be used to measure time intervals, generate delays, or trigger actions at specific intervals without manual timing in code. Timers play a crucial role in controlling the duration of each washing machine cycle, such as washing, rinsing, and spinning. Instead of using simple delay loops which block the microcontroller from performing other tasks, timers allow time to be traced in the background. In the PIC16F877A, there are three built-in timers: timer 0, timer 1, and timer 2. These can be configured as 8-bit or 16-bit counters and can operate in the timer mode, counting internal clock cycles, or counter mode, counting external events. To develop and simulate my project, I use two main software tools: MPLab X IDE and PixSimLab. MPLab X IDE. This is an integrated development environment provided by Microchip. It's used for writing, compiling, and debugging embedded C code for PIC microcontrollers. It helps in managing code files, building the project, and checking for errors before uploading to hardware or simulation. PixSimLab. This is a virtual simulator that mimics real PIC microcontroller hardware. Using PixSimLab, I was able to test my washing machine simulation, including the LED, keypad, motor, buzzer, and LCD, without needing physical hardware. Together, these tools allowed me to write and test my project efficiently in a fully software based environment. Now that we have seen hardware, software, and system design, let's see how it all comes together. Here's a demonstration of my washing machine simulation project using the PIC16F877A microcontroller and PICSimLab. This Now let's move into the project demo. Shows how the system responds to user input, controls peripherals, and manages timing using embedded C logic. Now let's look into the code written for project washing machine simulation in MPLabX IDE. First, we create a project file named washing machine, and under the project, we create header files and source files. The entire program is written in embedded C using the MPLabX IDE, targeting the PIC16F877A microcontroller. The code is structured to handle each stage of washing machine for powering on, mode selection, water level configuration to starting, pausing, and completing the wash cycle. It uses key features of the microcontroller, and this is the code for washing machine run program, water level screen, washing program display. And this is the main.c operation setting operational mode, again resetting it. And this is the code. Now let's see the project in the PixSimLab. First, we have to load the hex file in the PixSimLab. Let's load the hex file. Load hex. Open. Now first it displays press key 5 to power on washing machine. First step is to power on sequence. After powering on the simulation, the CLCD shows a prompt: press key 5 to power on washing machine. Once switch 5 is pressed, the system displays powering on washing machine. Let's press the switch 5. Now it will show powering on washing machine. This simulates the boot up sequence of an actual application. Washing program selection. Next, the user is presented with a list of washing modes such as daily, heavy, delegates. By pressing switch 4, we can change the mode: daily, heavy, delegates, whites, stain wash, eco cottons, woolens, bed sheets, rinse plus dry, dry only, wash only, aqua store. And these are all the washing program. We can select anything accordingly by long pressing the switch 4. Let's press long. Now it displays water level. After the program is selected, the next screen asks for water level, auto, low, medium, and high, max. By pressing switch 4, we can change the mode, and by long pressing it, we can select the mode. Now it displays press switch. For switch 5, it will start, and for switch 6, it will stop. Just let's check for the stop. By pressing switch 6, the program resets to the washing program selection. And now we can change the washing program again, and next screen it displays water level. Let's select low. We will spread switch 5 to start. It displays program stain wash and time. During operation, the system displays the current cycle like wash, rinse or spin and the remaining time. The fan or motor is turned on and off accordingly to the logic coded in embedded C using the timer module. This stage reflects the actual operation of washing machines in timed cycles. And now if we press switch 5, the program will start, and if we press switch 6, the pause. Let's press. Now the program is paused and the fan is stopped. If we press switch 5, again the program will start. Yeah, the program started. And there is another function. If a door is opened suddenly in the washing machine, and then the screen will display that the door is open. Now let's watch it. We have given switch 1 as the door, and the buzzer is also gets on. If the door is closed, again it will show the time. Now let's wait. After all cycles are completed, the CLCD displays program completed, remove clothes, and again goes to the washing program selection. When the program is completed, the fan stops and the buzzer rings. Now the program is completed, and this is the project demo. These are the outputs of the CLCD screen in the project. The first, press key 5 to power on washing machine, and powering on the washing machine, washing program display, then water level, and press switch start and stop, and function, and finally program completed, remove clothes. Conclusion. In conclusion, this internship provided valuable hands-on experience in embedded systems development through the successful implementation of the washing machine simulation using the PIC16F877A microcontroller and the PIC Genius board. By working on this project, I gained practical knowledge in embedded C programming, microcontroller interfacing, and the use of peripherals such as LCDs, buzzers, motors, and keypads. This project not only strengthened my technical skills but also enhanced my understanding of real-time system design and hardware software integration, preparing me for future embedded system applications. Thank you.